Good evening, everyone. So this is I think I took permission from Jairaj to use this word once exactly in my talk to say that I'm going to talk about state of the previous art, right? So this whole talk is going to be on the state of previous art. So sorry, twice. Um, okay, so I'm going to talk about one particular problem of ad exchange, probably slightly a bigger problem, or one of the more prominent problem of the ad exchange is it's an exchange end of the day. So there is one request that comes in. You have a bunch of partners that needs to be sent out. You have a finite amount of time, few hundred milliseconds, and then you will have to make a decision on whom to send to and how much time to give, and basically just bake in scale to that, right? So just about, like, let's say if you get one request that comes into an ad exchange, like approximately we can say that there are about 100 matched partners, right? Approximately. So now the scale factor that comes in. So like in each of our colos, we get somewhere around to our exchange somewhere around 1.5, 1.6 million requests a second at peak every day, right? So we have like 3 colos, so every colo will see around the same amount of requests. So this is some like a very high level diagram. What happens with that? There is from the publisher website or app, you get a request. Ad exchanges will take that, send it to multiple DSPs, demand side platforms, wait for some time. Either they will wait for them to come back, or like, let's say they will say that, okay, there is nothing available, right? So now, what are the constraints, right? So constraints is like, in general, we get about 300 milliseconds from the time request enters the system, right? So that means that we will have to do all of our processing, give as much as time to the DSPs as possible, which is another call over the internet, and then again, like once it comes back, do whatever you have to do and send it back to the like whoever's called us, right? And then there are there are infrastructure problems with DSPs, right? So they will say that, okay, I can only handle this much. You send me only, let's probably 50,000 requests per second or 100,000 requests per second. Do not send everything, right? So now it's up to you what you want to choose, but just make sure that you never breach this, right? If you breach above this, then I'm going to randomly throttle everything. Yeah. So basically, again. Not every single request would make sense to them, because this is some astronomical scale that is going to go in, and again, the DSPs are going to work behind multiple exchanges, so they will have a multitude of the traffic coming to them, right? And this is the other problem that we were solving, which AJ mentioned in the morning, like optimizing for the cloud egress, right? So because on the hypervisors, we have to send everything over the internet, and like if we send, like, let's say 1.5 million, let's say we make a very small conservative number to say we only send it to 30, 1:30, then that makes a massive bill, right? So that also is another factor there. So yeah, that's the thing. So we need a system that needs to stay a little bit intelligent, just so that we can make the best of all the constraints that we are operating with. We send what matters to the DSPs, and at the same time, we also keep our overall costs controllable. I mean, this also goes on with what Shantanu said, that it's a scale business, right? So one request would probably make very small amount of money, but a lot of requests is where you make a little bit of money. So, and again, like we didn't land at 1.5 million requests per second straightly. We started with around 300K requests per second, and initially when the journey started, it was all offline. We used to take a bunch of, again, this is a ASCII diagram exported as a PNG, so I don't know whether it's visible or not. So this used to be how we used to do earlier, right? So we have a bunch of data. We used to just create them into multiple segments. We say that for each segment, depending on all the historical trends, generally 24 hours, we do some predictions as to what is the relevance, apply the budget and the constraints, and then for a 15-minute window, you say, okay, how much is allowed, right? Basically a knapsack, and it says that Anything beyond this is an allow list. Anything below this, okay, drop everything. Just bake in a little bit in the little bit for the learning, just to make sure that okay, if something below the cutoff wants to move ahead, you have it covered, right? So this used to be the thing, and then I think honestly it worked well, right? I mean, it worked well for a good amount of time until the until the actual problems of scale started coming in, right? And here, everything is pre-calculated. It is loaded onto our serving machines as a maps. You would just do a, like we don't even do a remote call. We load everything onto the individual machines and do like a local machine lookups. So amazingly blazing fast. Nobody ever looked into, I don't think anybody ever looked into the latencies of that. Now let's come to the challenges, right? What were the challenges that we had? So as the data size and number of segments itself, right, they started growing, we started seeing some signs of brittleness in the offline, right? I mean, the job would run out of memory, there are job failures, and the prediction size started growing. And like any other engineering, what we said that, okay, if for a given set of segment length it grows, then we would drop one of them and reduce the number of dimensions, right? So that you have a smaller number of predictions for a given segment. A lot of optimizations happened on the offline side and on the online, because again we started seeing some memory pressures because this size was getting big. We needed bigger machines. But again, there is a limit on the hypervisors, how much you go for, and then, yeah. and then again, like, this was, I think, somewhere around 2.5 years back. Again, we grew probably around 5x by then, right? And then some of these problems started becoming more and more prominent. and this led to a couple of things, right? Because of like a very small number of features and this thing. So either we ended up sometimes over-predicting. We said that, OK, this may be profitable, let's include, because we just do not want it to be missed out. Or in cases of where we have a higher constraint, like only this much can be allowed, this is the thing that can go in, we ended up probably missing a bunch of pockets of actual profitable requests or the relevant requests. So now we call this system fan out. So now this is where we started the journey to say that, OK, we want to do a V2 wherein we want to challenge the kind of address the challenges of V1, and I think be very efficient in choosing what to send. And this is exactly also the point in time when the DSPs itself, they also started seeing strain on their infrastructure because they were just getting everything, right? They started saying that, OK, we need to control this. So now they have a lesser incentive to actually be very intelligent in doing that, because probably they are going to get the same thing. They can talk to some other exchange and get the same thing. So it was very important for us to do this, right? And then we said that, OK, we also, where as much as possible, we want to do for every request level, use as many features as possible and decide what we want to do with that. So yeah, and then since it was there was an online thing, so we just started. This was already probably, we were looking at around probably 150 to 200 billion requests a day, which was eligible to get into this funnel. So there was a large scale. A lot of iterations happened. Many model architectures were tried. I mean, we have our a few representation from our DS team here. A lot of work went in. And then, of course, like a lot of disappointments also, right? And sometimes that is where it felt that though the old system was, it seemed fairly slightly outdated, it was still doing reasonably well. To match that, it took a good amount of iterations, right? And good amount of iterations and probably a lot of testing, offline, online, both, right? OK, finally, we got something that works well. And it was that kind of moment where I think probably we had spent about 3 to 6 months, and then almost on the verge of saying that, okay, this probably is going to be very difficult and like that. And yeah, so now we have a model that works. It met a lot of this thing, and we were now using 50 plus features, about 10 million parameters, and yeah, and then we are able to predict for every single request that is coming in. So this is the kind of predictions that now happen per second. All of these are happening online on individual machines. I didn't made up those numbers. This is like a snippet from our Grafana. So until now, all good. But so this was one of those moments, right? So the model was working fine. So we said, okay, we are going to go ahead and enable it for a bunch of other partners. And the deployment happened somewhere around 12:10 UTC, right? And suddenly our per box throughput dropped by about, I don't know, around 30–40% or something. So we were doing somewhere close to 2,200 requests per second. That came down to around 1,700, 1,800 requests per second. Right? This was just start, and then the model was going through a multiple this thing. And this meant that our fleet now, I mean, we had anyway a horizontally scalable field, but the cost of doing the operations has started growing, right? So this is when, I mean, until now, I think the data science and other folks were under a little bit of a stress. Now that it is working, it was back to engineering. So yeah, so now there is a lot of cost pressure. So we say that, okay, our overall cost has also shot up, so we need to do something, right? So we started running profilers, and then like any other optimization thing, there are like few low-hanging fruits that's going to be available. All of them are taken away, but generally on this kind of systems, you don't see a lot of improvement by just doing that, right? Unless something drastically changes, they're all probably adding you 1%, 0.5% improvements here and there, but nothing much. And then one thing that we have done over the years is like, along with optimizing for the cloud egress, we also had put our hands into a little bit of other things where we run a very large clusters. We kind of have an on-demand profiling available through async profiler. So that's like we are kind of endorsing that all along. So all of our services will have something like an endpoint, like where every developer can just go and put this to see, okay, what is happening with the application, right? So now, yeah, I think this was used few more times to see, okay, where is the bottleneck, right? So we are kind of now bottlenecked on the dense layer computation, because the computations were large. We were just doing probably very naive calculations, right? And this is a homegrown ML library which Srikanth spoke about in the afternoon. So we have our own Java version of this. We are also fairly heavily Java shop. So now we need to find, okay, how do we speed up matrix multiplication, right? So I think we have our platform team along with this thing. So they were trying multiple libraries, like EJML was one of the things that thing came in. But again, I think the good thing with JVM ecosystem in general is that as long as you can keep up with the version changes, the underlying compiler and the JIT is moving very well, right? So even though it was probably EJML was applicable a few years back, but now there was nothing much. The out-of-the-box JIT compiled code was performing very well. And then we kind of bumped into this, right? So Lucene, sometime like Lucene is something which is, again, a very popular Java-based, probably heavily used engine. So they actually had taken up the incubating vector API sometime in 2023. They integrated it, they dropped it to that and said that, okay, if there are cases where explicit vectorization works, let's make use of that. Even though it's incubating, it is not probably expected to change drastically, right? And we said, okay, if it probably somebody like Lucene, I mean, which is highly regarded, can do that, I think we should give it a shot too, and probably we will have some juice. So yeah, so we went ahead. We just started with the double vector. We started the double vector, so I put a star there because just 1 week back, I think we were discussing that we are just overkilling it because it's too precise. Hardly even the training might not have happened here, so probably we are going to go to float vector. But yeah, but we started with that, and then there is always a general question saying that did it actually vectorize, right? So so it did vectorize, and it did give us a little bit of improvement. So we said, okay, are we I mean, there is that generic sense of achievement saying that, okay, you have used something new, okay, you see some results coming in, but it is still not, I mean, like all those stuff that you read, you still do not see that kind of acceleration in using the SIMD or all those things, right? So now we again went back to another tool, the kind of, okay, we said, okay, let's do some micro benchmarking to see do we still have really suboptimal or very badly written code, right? And then the first thing we just wanted to make sure was, okay, we wrote all the vector code. Is it really getting vectorized? Or is it still going to scalar code because, I don't know, maybe the hypervisor did not support it or we haven't configured it properly. But that was OK. It was using this thing. And then this is where I think we generated the assembly code. And of course, like nobody really knows how to read the assembly code that well. They just put it onto, I think, an LLM, right? And interestingly, it said that, okay, you should be trying out a FMA, fused multiply add, right? So that you can do both of that in one single instruction instead of doing first multiply and then adding it. We did that, of course, and it was available. It is available in JDK libraries, in non-vectorized code also for a good amount of time, but yeah, I mean, nobody really looked into that, unfortunately. But yeah, thanks to the LLM, we now know that even the JDK's math library has a FMA, and the vector library has it, right? So yeah, so now again, we were in a state where we said, okay, we are good enough, but still it was not very eminently satisfying, saying that, okay, we got a good throughput thing, right? Then again, I think we digged into some other code. We saw again in the Lucene thing, they said they did some manual unrolling, right? So we really let it to the Java's JIT to do the unrolling for vectorization, but then we said, okay, maybe if they are doing it, they might have done some experimentation. Why not? We should also try doing this and see what the benefit it may bring, right? Again, another unrolling of the loop. We tried with multiple things. Again, got a lot of assembly code, assembly printed just to see where we are and how it is. But it did really help, right? I mean, I think it did give another 20% more bump up. So yeah, so this is where we ended up with. So we started with around 3 operations per millisecond for the test workload that we were looking at, 10 million thing with around 50 plus features. So we went all the way till about 27 operations per millisecond on single thread. And this is a slightly older machine type, right? This is probably like, this is an AMD EPYC on GCP, probably about 5-year-old server machines class. OK. So now, what are the takeaways, right? So intelligent fan-out is very hard problem. I think it's not a very simple problem per se. I think we have a blog also on technology.inmobi.com around this. And then some of these are not purely technical problem, technical per se, but it is also more about how multiple teams needs to come together, right? I mean, especially the part where when things were not going good, it was very important for us to kind of keep at it. So that is where, like all factions of the engineering, like engineering, product, data science, analytics, all of them were kind of working towards it, even though there were multiple setbacks, right? So then, if as long as they are focused and there is a little bit of a safety net, then that could actually create magic or some sort of magic. Again, I think this goes back to the same thing, which just Pallavi mentioned. So just we need to pick what works best given the constraints. I don't think there is any rule of thumb per se. Maybe the pre-computed predictions work with a comparable accuracy given your constraints. I mean, there is no need for online perhaps, right? So, okay, so then our other thing, like making something faster, right? So this is the, like, I know a lot of people will have a very strong opinion about this, and there are, like, I think there are like few highly regarded talks or presentations around this on how to do the first one very accurately, right? I mean, I think it's still a very important aspect. It's easy to get kind of into a rabbit hole or get into a blind spot. But yeah, so you just need to always measure, profile correctly, being a very important part. Identify the real bottlenecks, make changes, again, kind of go through the grind again, right? I think as long as we are doing one well, I think most of the other things should be now fairly simplified. So this is this I thought of adding it here, right? So this is a kind of an output that comes in the Java micro harness benchmark, right? So micro benchmark harness. So that's what they say. It's an important thing. I think a lot of people should read that because this is what it means, right? So micro benchmarks are like our AR AI mileages, right? So it says that okay, your car can give you 26 kilometer per liter under A, B, C, D, or all different ideal conditions. But that never happens. But it's good to know that. Like it's good to know like what is if everything is all right, everything is fairly well set up, how much juice we can extract out of the given hardware, right? That's what the JMH can tell us, and it's also kind of helps us to, when you do this kind of micro benchmarks, it helps us to say whether we are moving ahead or we are moving 10 steps back, right? I mean, generally with some sort of like compiled languages, you don't know what all the compiler magic happening behind the scenes. So then we also kind of, along with all those things, for code like this, we need to make our benchmark code is also like just like your tests, right? So especially if we really bother about the test performance, we need to really benchmark them well. Otherwise, it's going to be mostly intuitions, right? And generally, intuitions are going to be wrong, especially when it comes to performance. So now, after this, so we said that, okay, we are going to add in our Omega's this repository, so we are going to have a benchmark module which specifically says that, okay, all critical module architectures that we care for will have a micro benchmark so that any new change or anything that we do, we can measure right here. And also, as part of the entire MLOps thing, we are going to make this available as part of training process and validation, right? So that when the model is being trained itself, they will know that, okay, what could be the expected latencies and the throughput constraints that it may run into. Generally, what happens is that a model comes through, it gets into the production, there is a small experiment starts, and then we see that, oh, the latencies are not something that we are looking at. So we may have to, again, either re-architect the model or come up with a different model architecture. So yeah, I mean, this is again a very heavily controversial thing. I think like the language war is like a little bit of overrated thing. I generally see that, especially if you go to any social media, that is like saying that every now and then there is a massive this thing. But one thing that at least we have seen is that as long as we can use the platform features well, understand it well, and very importantly, keep upgrading, right? I mean, I think we are talking about AI, but I think probably half of, or even more of the world's software still runs on Java 8 probably, which was released in probably 2006, 7 or something. Right? Yeah, that's all.